Net zero by 2070.
Okay, see, as I was telling you, 40 billion tons is the total CO2 emission around the globe. India currently produces 3 billion tons of carbon dioxide every year. We are third in the list of the highest CO2 emitters. Uh, China is leading it with roughly 11.5 billion tons of carbon dioxide every year. But there is a challenge with India is that it's still a developing country, and the rate at which our CO2 emission is increasing is roughly 5% to 6% every year.
Namaskar and welcome to another episode of the Professor Mahesh Podcast, your resource to help you make informed career decisions. As we like to think, this is your future simplified for you. This podcast is brought to you by IITM Global, an initiative of the Office of Global Engagement at IIT Madras. IITM Global stands for all of the initiatives that we would like the world to know about India and specifically about IIT Madras. Learn more about them and their activities in the link in the description below. Sustainability, global warming, climate change, carbon neutrality, net zero, ESG. I'm sure somewhere along you've heard some or all of these terms. This is going to have to become a way of life for all of us before we are able to live a satisfying life. To help us understand this space and to help us investigate and study what new careers are emerging as a result of this global change, what are the new careers being enabled by these winds of change. We have a guest, Professor Rajinish Kumar, who is the head of the School of Sustainability at IIT Madras. Welcome, Rajnish.
Thank you, Mahesh, and very good morning to you and your team. I see you have a wonderful team here.
Thank you, Rajnish. Let's start with your own journey. You are a chemical engineer. You studied to be a chemical engineer, and you are now very much invested in the space of carbon neutrality. So tell us about your early education and what got you interested in carbon as a problem.
Mm-hmm. Yeah, so you said I'm a chemical engineer, and that was by chance. Obviously, the rank which I had was suitable for a chemical engineering position in the institute where I did my bachelor's. So I joined it, and after a year spending in chemical engineering, I had an opportunity to move to some other branches, but I somehow felt that was not needed. Personally, I don't know. I know that you are doing it for the career options, but personally, it was not a big deal for me to get a job after 4 years of my education and all. I always thought that if I am learning something new in these 4 years, that is going to be good for me. So after studying 1 year of chemical engineering, I found that I am learning a lot of new things, and there was no need for me to change the branch.
Where did you study your early? Where did you do your early education?
I did my engineering from Pandit Ravi Shankar Shukla University in Raipur.
Okay.
So I belong to Madhya Pradesh. Those days, Raipur or Chhattisgarh was not there, or everything was Madhya Pradesh. So I did my engineering there. So as I was telling, after 1 year, I realized that there are a lot of things to learn in chemical engineering, and I just thought, why not learn this? Now coming back to how has been my experience in chemical engineering and how it has saved my career, and especially currently the carbon dioxide capture, or CO2, net CO2 zero, whatever we talk about. See, chemical engineering is it arms you with a lot of fundamental knowledge, and also it arms you. This is probably the only engineering which is very closely related to sustainability as well as net neutrality. If you talk about, say, a chemical engineers, once you start your day by brushing your teeth. So the brush which you are going to use, the toothpaste which you are going to use, pretty much everything is designed and built by a chemical engineer.
Sure.
And throughout the day, at the end of the day when you are going to sleep, you would need a proper bed sheet and a proper blanket, and pretty much everywhere you will find a chemical engineering coming into picture. So whether every aspects of your life you see a chemical engineer, basically engineering degree is needed. uh, for example, for the toothpaste, you will not believe that how much science is there in just for that toothpaste to remain that particular cylindrical shape. The right kind of rheology should be there, the right kind of density should be there. Under certain pressure, it should come out with that cylindrical shape. So all of these are really fundamental challenges, and you will not believe chemical engineers are trained to design some of these things. They understand the fundamentals physics behind it. They look at the chemistry, and since they understand the physics, and they are trying to basically develop some of these formulations. Why I'm talking about all of this, because what I believe is that the fundamental knowledge is very important. The thermodynamics, the chemistry, the physics. Unless and until you have that base, you will not be able to basically solve any problem of future or current. And carbon dioxide capture and utilization or sequestration, which we collectively nowadays call as CCUS, is very much important for net zero. So for you to contribute at this level, where something is going to be applied in industry or in real life, your fundamental has to be really strong. And I think chemical engineering provides you that kind of fundamental.
Wonderful. I think starting where you started, what was your PhD work on? What did you choose to do for your PhD?
My PhD work was on gas hydrates. Gas hydrates are something which is a crystalline form of water. But the interesting fact is that it's very much similar to ice, but it forms even at room temperature. So if you talk about water getting converted into ice, you need to go to temperature which is below 0 degrees. And at temperature below 0 degrees, you will be able to nucleate water into solid ice-like crystals. These are typically heterogeneous nucleation. If you want a homogeneous nucleation of ice, you have to go back to -36 or so at 0 degrees or below 0 degrees. Thermodynamically, it's feasible, but kinetically, it's too slow that you will be able to see some crystals at 0 degrees. So you'll have to probably go to -36, -35 for a homogeneous nucleation of water to ice. Now, this is very interesting, because now if there is different temperature just because of thermodynamics and kinetics play, in hydrates, we have one more component. In water alone, you have just a single component, water, which has to freeze. When we talk about hydrates, there are two components. One is water and one is another molecule, which could be a gaseous molecule. Any gases typically forms hydrate. So now, since you have improved or increased one of the component, the degree of freedom improves. It basically means that you should be able to form this crystal not only by modulating the temperature, but also by modulating the pressure, this particular second components impart. So you should be able to go to even a higher temperature than 0 degrees, and if you have the right pressure, water will convert into a solid ice-like crystal. Sure. Physically, there is no difference between water and ice, between ice and hydrates, but when you chemically look into it, you see that there is a guest molecule in each of these cages. So like what ice, which is basically hydrogen bonded water cage, hydrates also form with hydrogen bonded water cage. The only difference is that inside the cage, there is a guest molecule, which could be carbon dioxide. So why I'm saying carbon dioxide, because if you see that there could be a formation of hydrate with carbon dioxide. So let's say you have a mixture of carbon dioxide and nitrogen, which is typical mixture of a flue gas. Or if you have a mixture of carbon dioxide and hydrogen, which typically when you gasify the coal, you get this kind of a mixture. So the first question is that if I am going to use the hydrogen from a mixture of CO2 and hydrogen, and I have to first separate the CO2 out of hydrogen. Or if I am going to release the flue gas, that is mixture of CO2 and nitrogen, I have to first separate the CO2 and only release the nitrogen, otherwise CO2 emission will improve. So if you see, it's a process of CO2 capture. Now I am using these two gases as a mixture for hydrate formation, and if I preferentially allow only CO2 to go into the hydrate cages, then what I have done, I have converted a mixture which was two molecules which were both in the gas phase, and converted that into a molecule which is in a solid phase, CO2, which preferentially goes into the solid phase, and that way you will be able to separate these gases. So my initial PhD work was on separating a mixture of carbon dioxide and nitrogen by forming hydrates, which is basically a CO2 capture. And technically speaking, I am still continuing the same research, that is, I am capturing CO2 from a mix of gases.
Wonderful. So your journey to, on this path of sustainability technologies, started very early on.
Very early on.
Was there an interest in the kind of work you were doing even back then? Was that already sort of seen as a problem?
It was not, but it was assumed that this will become a problem. The reason was very simple. If you do, see, chemical engineers, the first thing they learn in their course is mass and energy balance. So the second thing which is what they are good at is that they understand the process from end to end, from a start where the raw material will come from, what would be the processes would be needed, and what are the product which you are going to get. So if you combine these two knowledge, you see that you can very well imagine that what we have been doing is that we have been digging all the carbon and hydrogen from under the earth. We are burning it from last 100 years more or less. We are utilizing the energy part of it, and the main product, which is CO2, which we are releasing to the atmosphere.
Yeah.
So this is a one-way path.
Correct.
We cannot, and if you do a proper mass and energy balance, it's very easy for you to understand that sooner than later we will have to worry about the CO2 which we are emitting into the atmosphere. And this is the reason why today we have been emitting 40 billion tons of CO2 every year around the globe. 40 billion tons is like not 40 billion kilogram or not 40 tons, it's 40 billion tons every year. That's the amount of CO2 which we emit.
Let's put that number in perspective. There are about 8 billion people, right? So each of us in some way or fashion is responsible for about 5 tons of CO2 in some way or fashion.
5 tons of CO2
per person.
Per person.
And the more wealthy countries obviously account for a greater
larger number,
fraction than some of the less well-to-do countries.
Yeah.
Okay. That's a good starting point. Okay. So now let's dig deeper into the problem. Let's put some semantics around this. Okay. So this carbon one-way street is not good. We have to stop it. Okay. So what are the ways by which you can pull this off? Before we get to the ways, let's define some things. What is carbon neutral? When can you say you're living a zero carbon emitting life? What is carbon neutrality?
See, the carbon dioxide is what carbon, when we say, we basically mean carbon dioxide in our terms today, because carbon is a solid. It cannot go to the atmosphere unless and until you burn it and convert it into CO2. Why it is important? Because if you burn a carbon, which is C, and when you are burning it in air, don't use the nitrogen but the oxygen. This is a combustion process. Carbon plus oxygen will burn to produce CO2 and energy. I think we are not interested in the CO2. This is why we are releasing to the atmosphere. The energy is what we are interested in. And where is the energy coming into picture? For everything we need energy. For example, I started with giving an example of when we start using my brush and toothpaste. The polymer which goes into the brush requires you to operate it at 300 degrees centigrade and 300 bar. Now, if you have to go to 300 degrees centigrade, what you need? You need energy. You need to burn the fossil fuel, which basically can go to that kind of high temperature. When we talk about 300 bar, it basically means we need compressors. Compressors would need electricity, and electricity will again come from burning the same fossil fuel. So you see, the challenge is not the CO2 part, but the challenge is that our demand or our greed for new materials every second, every minute has increased so much that we are consuming a lot more energy than what typically we used to consume, say, 100 years back. Okay. So when you are consuming a lot more energy and most of the energy comes from fossil fuel, then ultimately it is going to go as CO2, which is the main
it's primarily a lifestyle change.
Lifestyle change. Now the question is that how we will become net CO2 zero. Now the CO2 which we emit typically, roughly as of today, if you do a simple maths, it seems roughly 50% of the CO2 which we emit, Earth can capture it or sequester it or store it, whatever you call it, naturally. Naturally, basically, this CO2 will either go for the growth of the forest, will go and dissolve into the seawater and ultimately get converted into carbonates under the seabed. So 50% of it can basically be naturally captured. But the remaining 50%, which is coming mostly because of anthropogenic activities of all this energy requirement and all, has to be basically eliminated. Now, how do you eliminate it? The first option for you to eliminate it, if you don't want to do any change, you want to use the same lifestyle what you have been doing and the same infrastructure what you have already built, then the only way for you is to capture the CO2, 50% at least, and then put it back under the earth where it came from. Where it came from? It came from under the earth. Millions of years, all these plants which got buried deep down has got converted into fossil fuel. We are digging. We are digging all of that, we are burning, and we are releasing the CO2 and allowing it to go to the atmosphere. So it has to be captured and put it back under the earth, then the cycle completes. So the question here is that out of 40 billion tons of CO2 which we are emitting, the requirement is that 20 billion tons of CO2 has to be captured and sequestered. Now
you said half of it, the earth has a natural ability. What are the processes that drive that?
For example, a plant which grows with the carbon dioxide from the atmosphere and water from under the earth.
Right.
So the CO2 and water will get converted into cellulose, hemicellulose, lignin, and all of that. So since it's a large planet, we have 16 billion hectares of land on Earth, and pretty much 30% of that is covered by forest. So all the growth of the forest day to day will basically consume significantly large amount of carbon dioxide.
As well as the oceans and the algae.
So the second is the algae in the ocean, and also the CO2. We have some 70% sea water on this earth, and the CO2 solubility is slightly better when you have saline water, but that's not something which people are bothered about. What happens when the additional CO2 goes in? It basically forms calcium carbonate, sodium carbonate, and all of that, and it sinks as a salt. So there is a natural process by which there is always a chemical potential for carbon dioxide which is in the atmosphere will get dissolved into the water and ultimately form a salt and will sink down. So these two processes, major CO2 sequestration naturally happens by these two processes.
Okay.
There are a lot of CO2 emissions other than anthropogenic activities. For example, there could be some kind of landslide which would allow a lot of CO2 which has been buried deep down to come out. There are volcano eruptions that would allow a lot of CO2 to come out. There could be forest fire. You might be spending 100 years to build a forest, and then that entire 100 years forest can burn in like 2 months, 3 months.
Yeah.
You can imagine that so much of CO2 will come out of it. These are all natural disasters which will become more and more often when your global patterns changes, the weather patterns changes. So the global warming and all people talk about. So there are natural ways of capturing, and also there are naturally through which CO2 goes into the atmosphere. But humans are, these 40 billion tons I am talking about are anthropogenic activities. This primarily comes from the humans. So this is why I am trying to say that 20 billion tons if you will be able to basically eliminate, then we might be able to say that the amount of CO2 which is now emitted to the atmosphere is naturally being captured by the earth. So there is no net CO2 which will be getting added from the day we achieve this target.
So let's now bring this down to the individual scale or a small company scale. How do you define that the individual or a company is now carbon neutral?
Okay, so there are different CO2 neutrality scopes. So scope 1 calculation, scope 2 calculation, scope 3 calculation. Now in scope 1 and scope 2 calculation, which is currently is more prevalent, when an industry like Microsoft or Google says that by 2035 or by 2040 or by 2030 will become CO2 neutral, they are currently focusing on scope 1 and scope 2. Now scope 1 and scope 2 basically mean that I will be making my premise CO2 neutral. I would not really worry about where my materials are coming from, whether all those materials, see for example, as I was telling you, the brush example I gave, the production of the brush emits a lot of CO2 which is called embodied carbon dioxide. As soon as we get this mug or this mic, when it comes into existence, it has already emitted tons of carbon dioxide. So that comes as embodied carbon dioxide. But when I am using it over here, and if I don't account for the CO2 which actually is getting emitted because of this mic, then that is not a scope 3. It's only up to a scope 2. So for example, this campus of IIT Madras might be emitting some CO2 by burning electricity or some other fossil fuel. So we account for that, and that we call as scope 2.
Okay.
Scope 3 is like if some student is coming from 10 kilometers from away from the campus, so how he or she has come to this place. If he or she has cycled, then probably there is no CO2 emission. But if he or she has driven a car, then we'll have to account for the carbon dioxide which he or she has emitted. If there are 1,000 person who is coming every day in, then that 1,000 into that number of CO2 emission which has happened will have to be accounted for. That comes under scope 3.
So scope 1 says my activities per se would be carbon neutral. Yes. That means the amount of carbon I am emitting due to my direct activities are offset.
Yes.
Okay, so help us understand what are ways by which you can offset, or how do if let's say IIT Madras said I want to become scope 1 neutral.
Scope 1 and scope 2, they are little variation, but I'll tell you for both of these together. What IIT Madras has done is roughly 20% of our total electricity is coming from solar panels.
Okay.
So now I would say that if that 20% would not have come from solar panel, it basically mean that, let's say that is 1 unit of electricity I am consuming. If I am getting this electricity from coal, typically the numbers are 800 grams of carbon dioxide or 1000 grams of carbon dioxide per unit of electricity from coal.
Okay.
So for simplicity, let's say if I am consuming 1 unit of electricity, then it becomes 1 kilogram of carbon dioxide. So let's say IIT Madras uses 1000 units of electricity every hour. So it basically means that I am emitting 1000 kilogram of CO2 every hour. Now how do I make it zero? So one of the simplest way people have said for a scope 1, since we are not worried about the embodied carbon dioxide and all, I say that I have implemented 1000 units worth of solar panel on this campus.
Okay.
I am not counting the the carbon dioxide footprint of the solar panel or the cement or the structure which we have built. We will not take that into account. We will only assume that now the solar panel has come, how much electricity I am able to basically avoid, which is coming from the grid.
Right.
Typically the grid electricity is roughly 70 to 75% coal based. So now if I am able to produce 1000 kilowatt hour of electricity from solar panel, I would say that I have become CO2 neutral in terms of my electricity uses.
Scope 1.
Scope 1.
Neutral.
Yes.
So we can each think of our own lives by this definition and say individually I can say can I become scope 1 neutral?
Yes.
Is that possible?
It's not that easy. For example, for our campus, I'll give you the number, we want to become CO2 neutral in terms of electricity uses, but we have been able to achieve only 20% so far. I'll give you example of some of the other universities, what they do. For example, University of Sydney, I was there and I asked them, so what is your electricity, are you electricity CO2 neutral in your electricity uses? They say yes, 100%. So how do they do it? They basically source it from outside. They wheel in the electricity from outside partners. For that they go in contract for 20 years or so, and then they pay them a certain amount of money to basically produce that electricity somewhere else and basically exclusively sell it to the institute.
Okay.
That is one way of basically becoming CO2 neutral in electricity. Now, if I am going to extend it further, for example, this campus also has huge amount of plant life. Now, I'll have to say that, okay, there is out of 600 acres of land, we have 500 acres planted with trees. Now, what would be the CO2 capture potential of these plants? So, let's say if I don't have any plants over here, then this 500 acres is not covered with plant. It basically means that the 1000 kilogram of CO2 which I had emitted for my 1000 units of electricity, I don't put solar panels, but rather I plant trees. I don't go and pay someone else for electricity. I plant 400 or 500 acres of trees and calculate how much CO2 sequestration potential this plant has.
Sure.
And if it matches with 1000 kilogram, then we say, see, the other way of doing it, not by putting solar panel, doing it with the existing infrastructure, but planting a tree which will ultimately capture so much of CO2 which I am emitting somewhere else.
Very good.
So this is called carbon credit or carbon accounting. If I can do it within India, I can do it for any country.
Sure.
So you can emit CO2 anywhere, and since it's all connected world, I can sequester that amount of CO2 anywhere else in the world, and then we can claim that CO2 which has been sequestered there was funded by our resources. So I have become CO2 neutral. This is what most of these Microsoft and Apple and other big organizations are trying to do. That if they are seeing that it would be difficult for them to become CO2 neutral by the current process, because they have to depend on the same grid, electricity from the same grid and all, then basically they are implementing some of these processes or CO2 sequestration processes somewhere else around the world and claim that has been done by them.
Okay. So you either have to mitigate at source, or you've already made a little bit of a mess, you figure out how to sequester and clean up.
Yes.
So either mitigate at source or clean up. Those are the two options.
In this case, I gave you an example of moving to an alternative source. For example, from coal based, I am moving to solar panel based.
Correct.
Or living with the same existing infrastructure, but capturing the CO2 by either nature based solution or by some anthropogenic solutions, which we can discuss later in the discussion.
Very good. So this is the definition of carbon neutrality. Now, what is sustainability? What is your, I'm sure this can have many definitions, but what is your working definition of sustainability?
Sustainability is a very difficult term, to be very frank. Let me tell you, I come from a chemical engineering background, so I'll start with some thermodynamic example. Two examples I'll give. One example is when we talk about in thermodynamics, when we talk about behavior of gases, we say that these are real gases. But we don't know how to basically model real gases. What do? We basically first model an ideal gas. We say that there will be a gas molecule in a reactor which will have no mass, no interaction.
Okay.
If it has no mass and no interaction, we make it so simple that we know a model through which they will behave. Now we have understood the model through which an ideal gas behave, because there is no interaction, there is no mass, so there will be a set pattern through which they will basically move or will basically generate the pressure and all. So when it comes to real system, we basically modify this ideal system by adding few more parameters into it and say that this is my real system and this has so much non-ideality. So we always compare any real system with an ideal system and we look at how far we are from an ideal.
Okay.
We don't really measure the real because we don't know how to measure the real. It's very complex. So we don't know how to measure real. So we say that we know how to measure ideal and we will say how far we are from ideal, and that will determine how real I am.
Okay.
Sustainability is something like that. Unfortunately, there is a challenge there. Sustainability is that ideal line. We want to be there. Unfortunately, in this particular case, we don't even have a model which will determine what is that line. This model is every day evolving. So this model requires, say, 10 different parameters. We understand 5 of these parameters. 5 of these other parameters we don't even understand today. Maybe in future we will understand. So this model of sustainability, this curve or this line keeps moving up and up every day. As our understanding improves, today this line is over here. Tomorrow, if our understanding improves, this line moves up over here.
The reason this is multidimensional is because sustainability, from my understanding, goes beyond just energy use.
Yes.
Is that the main problem there?
It's main problem. I'll explain this by an example. I gave an example of solar panel. Let's say a solar panel. Now I am going into the scope 3 calculation. I'll tell you where the sustainability comes into picture. People say that you implement a solar panel and you have done everything. It's not true. A solar panel has embodied carbon dioxide. Why? Because silica has to be mined, has to be processed, and if you are going to basically put a solar panel, the silica which goes there has to be electronic grade silica. So it basically means the silica has to be first mined and then has to be converted into a metallurgical grade silica which is 99% pure. Then this happens at 2200 to 2500 degrees centigrade. Where that energy comes from? Right now from fossil fuel. Now once you have a metallurgical grade silica, then you have to basically melt it again with multiple other components, germanium, indium and all those in right quantity, and those has to be also mined from somewhere else and purified. And then you start creating a single crystal out of it. Slowly, again this entire process happens again at 2200, 2300 degrees centigrade. And by the way, these processes are not a single step process. Per pass conversion is hardly 10%. So you have to recycle it again and again. So you see the CO2 footprint where it comes from. So when we talk about sustainability,
the CO2 footprint comes from some heating needs or some processing needs.
Heating need, processing need, and these heating needs are such a high temperature that right now we only know to do it through thermal energy. We don't have a process through electrons, which we will discuss later in our podcast. So the point I'm trying to make is that, but let's say we have some embodied carbon dioxide which we figured out. And a simple calculation tells you that a solar panel will be able to pay back its carbon dioxide footprint or embodied carbon dioxide within a year. So once I have calculated everything, so much CO2 is coming out from the process of forming the solar panel, but the solar panel will operate for next 20-25 years and will produce so much of electricity without emitting any more CO2, because the production is not going to be any CO2 emission. So overall, if I divide it by 20 years or so, it comes out to be 1 year. Within 1 year, all the CO2 which it has basically emitted will be able to be paid back. But the question is that this is the plant load factor. I am coming to the sustainability part. What is the plant load factor of a solar panel? Is roughly 25%, less than 25%. In India, it's roughly 19% today. It basically means if I have to put a solar panel for my entire energy need, I need to install 5 times more than what I am going to basically need. Because the plant load factor is only 19-20%. So now if 1 year was the payback time of a solar panel for my energy requirement, it has become 5 years.
Right.
Now the question is that I have generated lot more electricity than I need. I'll have to store it for that remaining 18 hours when there will be no sunshine. So now I need batteries. Now the solar panel life is 20 years, 25 years, but battery life could be 5 years. So I need battery 3 times over during the solar panel lifespan. And these batteries will again require minerals, mining and all has to be recycled. So you add another 3 years for the batteries recycling and that many numbers. So it became 8 years. Now look at the sustainability point. Now what we have done, we are assuming that we will put solar panel in air. We cannot. It basically means some of the land which could have been used for planting trees has been now put for solar panel because I can't plant trees on those land anymore. Sustainability comes here. Now let's say if those plants were there or the forest was there, there used to be a lot of biodiversity. What happened to the biodiversity? Because if I am converting all of those land from a forest, let's assume, to a solar panel, I am going to lose biodiversity. Sustainability comes there. We cannot account for that from CO2 footprint point of view, just environment point of view. What would be the effect of losing those biodiversity permanently? Is going to be a question which should be asked. This is where sustainability comes into picture. Okay. Now, for example, when we talk about putting so much of solar panel, then so much of light is going to get reflected also. Not everything will get absorbed.
Right.
That will increase the local temperature. That is going to bring the change in the cloud pattern, the weather pattern. If there would be a forest over there, we will be able to attract cloud, but when there is going to be a solar panel over there, we will repel those clouds, same cloud, because it will be much more hotter and it will go and condense somewhere else.
Sure.
How do you account for that in CO2 footprint? This is where the sustainability comes into picture. It's a complex product. That's why I'm saying sustainability is very complex. Every time you look at it, you see, oh, this is something which we have not accounted for. This is something which we have not accounted for. And every time you'll have to keep accounting for that. And this is why this is one line which keeps moving up, because as our understanding goes better and better, this sustainability goes much tougher and tougher. But in that process, we are basically aware that we have not reached there yet, and we have to do more so that we basically reach there.
The awareness itself is a big victory in some way. Yes. Let's define a third term, circularity. Yes. Okay, what does circularity mean?
I think for an engineer, I'll tell a circularity basically mean moving. See, let's say solar panel again. I'll use the same example. When we said that solar panel requires 2200 degrees centigrade twice and 10 times the process which will have to run for getting some significant yield. All this is basically done which will require a lot more energy. But if the silica has already been purified and has been put in solar panel, 20 years down the line it has degraded for some reason or other. When I am going to recycle this material, the same amount of energy would not be needed. Maybe the amount of energy which would go in recycling the material and making a new solar panel out of it would be say 50% of the total energy which was initially needed from the raw material which was much more impure. So this is the advantage of circularity. If I am able, for example, currently in US, they have built their infrastructure from last 100 years. They don't need to basically build new steel plants. They are just recycling their old steel which they had built over 50 years, 100 years back, which is currently being scrapped. They are just recycling those steel and they are getting their steel. So their CO2 footprint for fresh steel production will be much, much smaller than the CO2 footprint of country like India and China, which is still building, because they will have to build from scratch, from virgin raw material. So their CO2 footprint will be much higher. So circularity allows you to basically reduce your CO2 footprint significantly, not only CO2 footprint, but also allows you to be more sustainable. Because if I am not taking those minerals from the earth, it basically I am leaving those minerals behind, and it will allow me to use it later, 100 years, 200 years down the line. If I am consuming everything right away, then we are not sustainable.
It appears that circularity may be the shortcut in some sense to carbon neutrality.
Yes, it's needed. Because CO2 neutrality and circularity has to go hand in hand.
Okay.
Because even that remaining 50%, see, there is another challenge with circularity. See, when nature makes a material, some material which is very reactive, nature has kept it separate. But when humans make a material, we are not bothered about the nature. We are only bothered about my utility. For example, when I am looking for a polymer, I see whether this polymer has a color. It does not matter to me whether it should be green color or red color, but we still put the color because it attracts my eyes.
Right.
But when I have to put the color, it basically means I have to add some additives in there. For example, a dye gets added. If I am talking about a polymer which should not melt when I am supplying hot water, it basically means that I have to vulcanize this rubber or this plastic by some other molecule. Nature has not done it for us. So it's much easier for you to separate two molecules from nature because they have kept it separately. Humans, when they mix two molecules together, they have already bonded together so strongly. Now you have to separate it out. You require a lot more energy. So even though circularity technically should allow you to reduce your energy footprint or your CO2 footprint, but then since it's human made and we don't care about what kind of material should be mixed and what could not be mixed because we are only worried about the final quality of the product, in the process we have mixed so many material in such a way that separating those out probably at times could be a lot more expensive, lot more energy consuming than actually getting a new material and starting from the scratch. So this challenge is also there. And PVC, for example, very difficult to recycle, but polyethylene you can recycle easily because it's virgin. It's just carbon and hydrogen. But once I am adding chlorine in there, or if I am using fluorine in there, if I am using bromine in there, this is needed. Bromine is added because I want my circuits to be fireproof. All these electronics to be fireproof. So I add bromine in there. Too much of polymer is there with bromine in there, and how do you separate it out once you have already reacted it?
So it can only be used for that use case one more time, at best.
Sometimes it is not.
Even
you will have to separate it out and use it for a different case, and for that you will have to use a lot of energy.
Okay.
This becomes a challenge many a times, and as a chemical engineer we always say that there is nothing to purify. When we say we will purify or we will extract something in something, no. Some impurity is there in one solvent. Let's say I have a water which is contaminated.
Yeah.
How do I separate it out? I will have to use something else where that impurity will come. It will go from one stream to the other stream. This stream has got purified, but the other stream has got contaminated. And typically what people say, use water. How much water you will use? Everywhere if you start using water, do we really have so much of water? Because they used to say, oh, water is something which is God made. You are not creating yourself, so there will be no CO2 footprint. So this is why water seems to be the best molecule, but today water scarcity is becoming a big deal. So it seems circularity also has to be properly looked at, not necessarily that every process which is basically out there is CO2 neutral or is good for the environment. Lot of processes looks pretty bad when you do energy analysis and mass balance.
Very simple, nice definition, Rajinish. Let's look at the big picture for a minute. India has made a promise to the world that we will be carbon neutral or net zero. I don't know, you should correct me. Is it carbon neutral or net zero?
Net zero.
Net zero by 2070. What does this mean and what is our high level plan?
Okay, see, as I was telling you, 40 billion tons is the total CO2 emission around the globe. India currently produces 3 billion tons of carbon dioxide every year. We are third in the list of the highest CO2 emitters. China is leading it with roughly 11.5 billion tons of carbon dioxide every year. Second highest is US with roughly 5.75 billion tons of carbon dioxide every year, equivalent of carbon dioxide every year, and India is roughly 3 billion tons. But there is a challenge with India is that it's still a developing country, and the rate at which our CO2 emission is increasing is roughly 5% to 6% every year. Last year compared to the previous year, we have consumed 8% more coal. So that clearly tells you that if our coal consumption is increasing by 8% every year, there is no reason for us to believe that our CO2 emission will not be improving by roughly 5% every year.
Sure. But it's actually a good point to look at our GDP growth itself is on the order of 7 to 8%.
Yes. That's the reason. See, most of your GDP growth, by the way, I will talk about it later, but GDP and sustainability are at cross with each other. So this is the bigger challenge. But anyway, the point I was trying to make and the question you asked whether we are doing good for 2017 CO2 neutrality. So let me tell you. So this is why it basically means that if I have to plan for it, 3 billion tons now, 10 years down the line, it will become 6 billion tons. So by 2035, we are talking about 6 billion tons of carbon dioxide. Now, as I was telling you, 50% of it has to be captured. how do you capture 50% of it? Basically mean that 3 billion tons of CO2 has to be captured. Today we are doing zero. Virtually zero. Means if you talk about billion tons and some few tons is like no number at all. So that basically mean that we need to basically first from 5% we have to go to 4%, 3%, 2% and become 0% at some point of time. It's not going to be that easy. It will take a lot more time, and this is why we have our target, mid-term target, that we will have 500 gigawatt of total renewable energy installation. Right now coal-fired power plant installation in the country is roughly 240 gigawatt. And the renewable power electricity generation is roughly 270 gigawatt. So we have, good news is that installed capacity of renewable is actually now already higher than
Cool.
But if you talk about the grid, energy mix in the grid, and this is where the people should worry about. See, if you talk about a coal-fired power plant, typical number is roughly 80% plant load factor. It basically means that your installed capacity is 240, you would be roughly 200 gigawatt producing any day. Our consumption fluctuates based on the weather, but our fluctuations are anywhere between 230 to 280 gigawatts. So it basically means our installed fossil fuel capacity is only 30 gigawatt less than what we consume in the entire year. So that, what is that 250 gigawatt of renewable doing? Only 19% of that is actually coming into our energy mix. So that clearly tells you that renewable energy, the challenge has always been that the installed capacity has to be significantly large. And let's say if I am going to convert everything to renewable, what would be the installed capacity needed by 2050? Roughly 3000 gigawatt, keeping the plant load factor into account. Today, how much solar panel installation we have? 100 gigawatt. You see the scale of that work or infrastructure development which is needed to go from 100 gigawatt as of today, 129 roughly, if I am not wrong, to something around 3000 gigawatt by 2050
Of installed capacity.
installed capacity is going to be a significant challenge. Currently we are increasing our renewable installed capacity by roughly 5%. Our GDP growth is roughly 7%. So that means that there is still a gap of 2%. So it basically means 2% of that additional GDP is being installed right now through fossil fuels. And once you have installed something, you can't just stop using it 2 years down the line. It will be used for next 20 years or so, for at least you to pay back all the money which you have invested in there. So these are some of the challenges, to be very frank. That much of solar panel installation for such a large country is not going to be that easy. We need certainly a space. That's something which I don't think India would bother about, but the amount of investment which is needed is certainly significant. And there will be not only that installed capacity which would be needed, you need to basically store this. Now storage options are either batteries or hydrogen as of today. There are other long-term storage options which we will not talk about today, but both of these requires huge amount of investment. Hydrogen will require huge amount of electrolyzers, installations. Challenge is the cost. I'm sure most of us are already aware that hydrogen production is not a challenge. We know the way to basically produce hydrogen, but the cost at which it is available, probably not many people can afford it today. So these are the challenges. But I still believe 2070 is a target which in 2 generations, we have 2 generations actually, 2070 does not look real like too far. So in 2 generations we should be able to achieve it. It will be challenging, but we should be able to achieve it.
And to get there, you need 2 things. One is, as you said, capital to invest. But you also probably need ideas to improve the plant load factor, to improve the technology mix that will make this happen. That's where smart brains can play a big role, can't
Very
they?
important actually. You talked about the mix, which is when we talk about renewable energy, that mix is very important. How do we mix it appropriately? How do we optimize this mix so that we are able to improve the plant load factor?
Yeah.
And that is where lot of AI and grid management and all of these new job roles which we talk about. See, I'm talking about the challenge now, but let's look at the opportunities over here.
Yeah.
See, 245 gigawatt of installed capacity of fossil fuel based power plant has not happened in a day. It took almost 7 decades for us to do that. Currently, if I'm not wrong, 5 million people are employed in this. But then this sector is already saturating. It basically means there is no new job growth which is basically there in some of these sectors. And if you continue doing it, it basically means that our young people will not be able to employed in some of these sectors because there is already not much of growth, and there are most of this has already happened, lot of automation has happened. We should look it as an opportunity. Now the energy transition tells you to basically change all of these, rebuild everything from scratch. Now when we talk about rebuilding everything from scratch, imagine the job generation which it is going to create. If I am going to install 3000 gigawatt of solar panel by 2050, it requires huge amount of human intervention. And each of these steps would require a lot of job creation, and this is what our young students should be interested in, that energy transition, however bad it may look like, but if you look it from job perspective, it's going to be better for them.
We will come to that and dig deep into that part. Okay, but before we go there is one more term that is usually used mostly in the corporate parlance: environment, sustainability and governance, or ESG. Some people use social and governance, but environment, sustainability and governance, ESG. What does that mean? What is the mandate for a company to be ESG compliant?
Right now there is reporting which is done. BRSR reporting is there, where you basically report how much CO2 you are emitting and what are your social compliances and all, what kind of governance model you have. But for simplicity, let me again take some example. For example, I am going to build power plant. Okay, environment basically means that if I am going to build this power plant, if I am going to do it by solar panels and all, it will be better. So we know by now that what is the CO2 footprint of a solar panel, what is the CO2 footprint of a coal-fired power plant, so which one I have to choose. That's very well known, and environment basically gives you enough data that if you choose solar panel, it is going to be better for you. Social, as an engineer, you don't understand social that well. What exactly where the social comes into picture? The social or the sustainability part of it comes into picture from the human resource part of it. If I'm building this plant, the people which we have basically hired, are they treated properly? Or they are running around even to get drinking water? Because see, the same plant, I'll tell you, the same plant where the permanent employees have plenty of drinking water available, but when there is a person who comes to build their unit, just for drinking water they have to run here and there. For 1 kilometer they will have to walk, and they will have to carry a bottle and fill from somewhere. That comes under the social aspect. Are we giving them enough, I would say, respect that they are building it for us? Are we careful that the people who are being contracted for this kind of job are doing it with good amount of gender equality? These are all comes under social of ESG part. The governance is all about, if we are putting a plant, let's say the option is to also put a nuclear plant. There also the CO2 footprint is very low. But this is where the governance comes into picture. I might have a very bright idea of putting a nuclear plant, but the people around this area where I'm putting the plant, if they are not ready to have that plant among them, then what is the point? This is where the governance comes into picture. Do you know that you will be able to govern it and make this organization profitable? Whether there is a social acceptance of this particular plant nearby. If you don't listen to them and still go ahead and do it, there is no guarantee that you will survive. There would be a lot of social unrest and all. The governance comes into picture whether we are cutting corners. Who will tell you whether you are cutting corners or not? There should be some governance model that this has to be done. If this plant has to be created, there has to be this ISO certification through which this process has to go through. So this ESG is looks into all the three components together. The environment, just fixing environment will not ensure that your social and governance is taken care. So you'll have to separately look for the social responsibility as well as the governance part of the responsibility. This is why this ESG reporting is becoming a big deal. In an equal society, we expect everyone to be treated equally. So each of these parameters has to be treated equally. Okay. Engineers, we don't really understand too much, so we always focus on the environment part, and social and governance goes out of the window. But I was giving you the data of that job generation. 5 million people have been employed in certain sector. But if you talk about the service sector, which is where the social and governance comes into picture, that is 10 times more, 30 times more. So that is where there is more job generations and more job opportunities. So this should not be ignored. This is something which should be the message given to the young people who are aspiring to become engineers. But these are the areas where they don't understand much, and this is where there are more majority of the job which are available.
Wonderful. So so in this whole space, we've already talked of jobs in 2-3 different flavors. One is ESG and the BRSR requirement, and there is an army of people are going to be required in all of the tens of thousands of companies to make sure that we are first reporting and second becoming increasingly compliant. What would be a training that you would suggest that this individual go through to be ready for careers in that space?
See, obviously, if you look at it from the training point of view, currently not much training is actually being given on these aspects.
The School of Sustainability does a little bit, doesn't it?
So School of Sustainability, and before that also, before School of Sustainability, we had incorporated few courses to basically expose students to ESG. School of Sustainability right now is running a program for sustainability of Indian businesses, which are basically being people who register there are mostly professionals, working professionals. They are already working in different industries and they want to learn more so that they will be able to comply better for all the ESG reporting, and later on they will have to ensure that their organization goes in that direction. But personally, I believe still individual departments, whether it is chemical engineering or civil engineering or mechanical engineering, will have to basically build the sustainability component in each of their courses. Because see, sustainability, even though looks like a different topic today, but some 10, 15, 20 years down the line, it will not remain a department in itself. Every department person would be expected to know sustainability. So this has to be built in our core courses. The elective courses should basically focus, one particular chapter or portion of this particular course should focus on the sustainability aspect of whatever is being taught. Unless and until we go in that particular direction, I think we will not be able to do justice to this aspect of our.
But are they primarily engineers? Is an engineering degree required for them to be an ESG professional or not required?
Not today. But if you are an engineer, you will be able to see, for example, a chemist or a physicist. They don't look at a problem from a life cycle point of view. A system thinking engineers have. They are the one who are expected to solve a problem which is supposed to be there for the society. In chemists and physicists basically look at a very small problem, they go deeper in there. But engineers are supposed to be much more broader. And sustainability is a problem which cannot be basically, you cannot tie yourself within a small frame that, okay, this is what I am going to make sustainable. This is going to be done for a life cycle of the entire process. So I think engineers are more suitable to take up these jobs of sustainability. Engineers which are primarily engineers, but later on they have been trained on sustainable finance. They have been trained on governance, which basically allows sustainability. So it's like additional degrees which will come to them, but the fundamentals of sustainability will happen during their 4 years of engineering education. That has to be the way forward, and every department has to basically relook at their curriculum to ensure that every course they are basically doing, whether sustainability has ESG component has been incorporated into it or not.
So what you're suggesting is 4-year engineering studying students, while they are studying engineering, can take these additional modules, courses from various outlets and become, let's say, an ESG professional or carbon markets professional. Let's talk of this idea of carbon accountant. We talked of net neutrality. Somebody has to be able to do that. How does this carbon accountant idea work?
Right now people are using some softwares, but I think one has to go a little deeper there. See, when we say that I am going to cut my CO2 emission by 50%, the question is that, okay, do you know how much you are emitting?
Yeah.
So it's the first question people will ask. This is what is happening currently through BRSR. This is a reporting. Government is asking all the organizations, you report how much you are emitting.
Okay.
And right now there is no penalty for you to report whatever you want, and they want you to believe that there will be no penalty ever. So you will be able to report it correctly. But then when you are trying to report, it basically means not everyone can report. If they want me to calculate, I might look at a particular process, this is what I understand, I'll calculate it properly. But then that may not be the complete calculation, as we've talked about scope 1, scope 2 and scope 3. So now this is the concern. If someone has to first count all the CO2 is coming from a process, that person should understand the process. If he or she does not understand the process, then he will not be able to basically count all the CO2 coming out from process. So it basically means this carbon accounting cannot be done by a single person. There has to be a team of people. And each of these person in this team will have their own area, that this is where you will basically see all the carbon dioxide coming from. This person will look at the CO2. So basically this is going to be a team effort, but there should be a leader of this team who would understand the entire life cycle analysis or the entire value chain, who would be able to ultimately say, yeah, this is the number which seems to be more accurate compared to the number which is. Now once you have accounted that, okay, so much of CO2 is there, now how do you ensure that part of this CO2 is being sequestered? Now there are multiple ways, as I told you, 2 ways. I gave an example that you can go to renewable route, or you can do existing things, but you can capture and then sequester. The accounting person should be able to do a proper analysis, economic wise, sustainability wise, and tell you this will work better for you in long run, giving your business requirements 20 years, 30 years down the line. Now these are skills which you need lot of exposure with current job in the market and all, and this is why I think these skills are not very much suitable for a young person who has not worked for industry. These skills would be more suitable for people who have had some experience in industry, and then he or she understand the entire process well, and then come back to the academia, or while he or she is working, take some of these courses and upskill himself or herself, so that they will be able to deliver slightly better.
Very interesting. So you are suggesting that there is not just the accountant audit side, but there is the advisory and almost engineering a new carbon future for companies. Yes. So there are careers on both sides of the coin in some way. Now you also said some experience is a good thing. Can students gain that, you think, from internships and some early career opportunities?
Certainly, I think in India anyway we are too bothered about getting job as soon as possible and all those things. I think I'll give you an example of management courses. In India, people don't bother about industry experience and all. They just finish their 4 years of degree or 3 years of degree and go for management, and they go into management role without having any industrial exposure. And they do equally good probably because this is what is very prevalent in India. But when you go to other countries, Western countries, you will not see many people doing management degree just after their engineering or their graduation. They would go and work in industry for 4 years, 5 years, 6 years, and then come back and then learn some of these managerial skill, and then they go back to contribute better. Both of these works actually. So what you are pointing out is that if you are saying that, okay, no, industry exposure is not needed and it can be done through some internship and all, possible. But I would still say that that exposure which you will get working with so many people, because it's not only the environment side of sustainability we are talking about, it's the social side and the governance side, which is typically not very easy for you to learn unless until you have spent some time with people. What you can learn from the books or by interacting with few people, your friends or your faculty, is the environment side. You can very well do that. But the social side and the governance side, which is required for you to be doing a better contribution, will always be missing if you do not have that right kind of exposure. So if you are trying to go into a job which is more technology oriented, you probably don't need to be trained in an industry for 4, 5 years, 6 years. You will still be able to do. But if you are looking for more of a managerial role, where you are looking for sustainability managers, or managing the sustainability of an organization, it is much higher role with a lot of layers. So
that requires some growth to get there. At the entry level, getting a good grounding in basic engineering to be able to do mass and energy balance to
thermodynamics.
start.
I think people does not give too much of importance for thermodynamics. It's very important.
Okay.
I didn't touch upon it, but it's very important. For example, I'll give you, since you talked about it. See, when we talk about carbon dioxide capture, where you are capturing your carbon dioxide from? Are you capturing from the air, or you are capturing from the stack? Because if you are capturing from the stack, the entire calculations or the technologies are going to be very different
compared to when you're capturing from the air.
Right.
Now the challenge is that if you don't understand thermodynamics, you will believe that both of them would be equally effective.
Right.
It's not true. Because when you are capturing from the air, you are capturing 1 molecule of CO2 out of 2500 molecules of nitrogen or oxygen.
Yeah.
But when you are capturing from the stack, you are capturing 1 molecule of CO2 out of 9 or 10 molecules of oxygen and nitrogen. Now if you don't understand thermodynamics, you will believe what is so big deal about it. Here also it is capturing, there also it is capturing, but people who understand the fundamentals, they will say that that will be 10 times more energy intensive compared to this, because your concentration here is much higher of CO2, so that you will be able to use a molecule which is much more greener compared to a molecule which you might need to use from direct air capture. So you see, the fundamental knowledge, if you do not have, that domain expertise if you do not have, you may claim that I have been able to do this, but you will not do a good job and you will not be really sustainable. You might be able to do some intervention, something will come out of it, but sustainability will not be one of that.
Okay, good. I think we've talked of 3 different flavors of people that are required. One is energy auditors or environment and sustainability auditors, environment and sustainability engineers and managers. And there are also energy engineers who are managing these vast solar farms or wind farms or tidal energy farms. So these are all new careers that today don't exist. Maybe wind farm manager or wind farm engineer, solar farm engineer are a few here and there, but the vast majority of the energy, the green energy streams that will come on board are still in the development phase. You talked of hydrogen as a means of storage and transport. We need an army of people alongside electrolytes. Yes. Right? So that army of people are still under trainings, and these are all absolutely amazing opportunities for anybody to step in and be a nice green engineer in some way, be a positive contributor. In all of these, let's talk for the last part in terms of what students can do to train themselves mentally. Like, how do I think of this training? There are opportunities, there are modules and resources available, but what do I think about in my own career to say I am ready for this career? What should be the driving force?
Yeah, so I always believe that today young generation are really, they want quick information, so they typically go to videos. What typically happens with videos is that in videos you get the end points, but how you have reached to those end points is missing actually. So I somehow believe that the fundamentals has to be really strong for you to be good for any job which you are interested in. Ultimately it has to depend on your interest, but if you are really interested in working on sustainability or environment or social governance and aspect, you will have to basically start reading from the books. The fundamentals has to be really strong. As I was telling, if I am going to work on as a carbon dioxide capture engineer, which is not existing today. Today, no industry employs an engineer who will only work for CO2 capture. In fact, in India, there is only one pilot plant at that scale which is running, which will train you to do something like that by NTPC, which is called Vindhyachal Super Thermal Power Project. The place is Vindhanagar, and they have a unit which captures 20 tons of carbon dioxide per day. Okay, so when you talk to a student, he or she would say that, okay, fine, I know how to capture carbon dioxide. Knowing is not sufficient. What is the challenge here is the kinetics. See, every minute tons of carbon dioxide is coming out. You may know how to capture, but do you know how to capture 1 ton of it every minute? That is the question actually. See, if you really want to make a difference, and that too to the industry, you will have to understand the kinetics of it. Thermodynamics, many people understand it and they think that, okay, this is all is needed, but it's not true. Why all of these are not going to the public domain today? Obviously, one aspect is the cost. No one knows who will pay for it, and someone will have to pay. That is still not clear. But the other challenge is the kinetics. Not a single pilot plant which is basically across the globe, which is running today, has been able to capture even 1% of the CO2 emissions. Now that basically means that we know the process, that it works, but we do not know how to scale it up at that level. Now this is where an engineers are needed, because the concept of time or the kinetics is not there in chemists typically. They only typically look at the thermodynamics part of it, which is oblivious of time actually. If it happens they will say that 300 milligram of CO2 can be captured in per gram of my material. What, in 1 second, in 1 minute, in 1 hour, in 1 day? How long it takes for you to capture so much? Because if you do not have the timing concept, then you cannot size your plant.
Sure.
Sizing requires that time. Now, who will tell them? If you are going to do this, a video will not teach you all of this. You'll have to go and read the book and try to understand what are the parameters in each of these models which have gone in. And if time is not there, how do I bring the time? Where it comes into picture? So this understanding cannot happen unless and until you are reading it properly.
So the high level advice is become a reader, understand the big high level problem and the micro scale solutions, and then see what you can do to progress along. Rajinish, this is obviously a topic that we can go on and on. I really think we should do one more episode somewhere down the line, but this has been a fantastic conversation to get our audience introduced to carbon neutrality, net zero, sustainability, ESG, and all the different flavors of careers that are now hardly even known to people, as you said. Thank you for coming on, and thank you for this wonderful conversation.
Thank you. I hope this conversation helps the student. My intention was to tell that there is no hurry to go for a job. Learn as much as possible, because this is the time, at this age you learn. You can learn for many more years, and there is no fun in just going and start working. Learning is much more fun. So spend as much time as you get to learn, so that later on when you start contributing, you will basically do really wonderful. Thank you.
That's a great message to leave our audience with. I hope you all have picked up where this world is headed. There is so many new and exciting career directions that don't even have names today. Forget people, forget training modules. So learn where this field is going, and make informed career decisions in your own lives. Until we meet again, be well, do good, and keep in touch. Goodbye.